Okay, so welcome everybody to this very special occasion for an alumni lecture. Here is Adrià. Good afternoon, Adrià. We are very happy to gather all you, so the students from this year, but we told them that we will have this special session and the opportunity to have this feedback from alumni, from past students, and see a little bit what they have been, the cool stuff that they have been doing. And we expect this should be like a tradition. It's the first edition. We are very happy for this. Actually, the idea was from Giacomo. Okay, he was like very enthusiastic and very happy with things he was doing, and we said, yeah, let's make it a thing. So thanks, Giacomo, for the idea. And please let me introduce to the students, to Joshua, very nice, very skilled American student, and Giacomo is from the first edition, and they really pushed to frame the master. Adrià also from the first edition, and he's working in probably one of the most technological factories in Catalonia. Marc, but he will not be able to join. And Christian, he has been diving into hard computing, and we think it's a very nice outcome. So please, Joshua, if you want to start.
Yeah, thanks for the opportunity just to start. You see the screen?
Yes.
Yeah. So I was in the master's maybe 3 years ago. Found myself back in Kansas City, my hometown, where we have Huft, this design and fabrication firm focused on architecture. But what's been really beneficial is that they have a rare combination of a fab shop with their design studio. So we're not just architects here, we're fabricators, interior designers, and artists, which has been a real nice bridge to kind of flow between the studio and fabrication for especially digital fabrication. It's just a little short intro of what our place looks like. It's a nice glass wall that divides us, so we really try to collaborate a lot. And I've added one project since Marc wasn't there, so hopefully I'll get through all these pretty quickly. But all these projects focus on essentially digital fabrication, from design to how we can use technology to help us efficiently create unique kind of installs. So this first one was a feature wall, kind of give an overview of the building, which I kind of was asked to install a feature wall after the design, but taking ideas from the concept they had already established. This building was kind of along a river, as you can see, and there was an old watermill on site. So just kind of an interview, but getting into kind of the concept of where these walls are going and what could drive really the overall design. Because again, thinking just about watermills, these beautiful kind of interior shots of how they functioned, especially these large gears and wheels that kind of made them work pretty efficiently. So our first wall, just kind of tasked to fill in around an elevator entry at the lobby. These are just diagrams explaining. There was a lot of iterations, but these were kind of the final diagrams that led to what we wanted to create. So kind of taking our full canvas, mapping some gears on it, dividing those into kind of strips and regions, and starting to get these kind of varied lengths and dimensions and depths with a bunch of wood units that we had to start thinking about, okay, how do we kind of piece this together in our fab shop, and then be able to send to site in pieces, but for a clean install. it's kind of a rendering, but I'm going to walk through kind of the whole fabrication process and how parametric design kind of helped us organize and group and efficiently get this to the site. So this is kind of, boring technical drawing, but produced parametrically from our studies, really allowing us to group and understand where we're going with this before we kind of had our machines start to cut a bunch of these wood units that created the overall composition. And additionally, how our fabricators could easily take a ton of pieces and place them where they needed to go without thinking too hard. So kind of what you're seeing on the back is, again, straight out of the parametric script and programmed to kind of help locate where a bunch of holes would go, essentially to receive a bunch of wood units. It kind of looks chaotic, but there's actually an order to all these holes if you kind of look closer that follow the kind of gear mapping design on the front. And then a quick little detail view before I get into images, but something that we found that would help our fabricators kind of guide their process of attaching all these singular units was taking our smaller units and kind of routing a notch into our back panels. Those really kind of led the way to somebody to just place a bunch of repetitive units first, and then all of our unique units directly next to those as they worked kind of from left to right. Again, pretty helpful parametric design and allowing us to cleanly and orderly output a bunch of stuff for kind of direct geometry to our CNC router that we have in-house, and keeping those in order for then our next step of somebody to put all these kind of pieces together. So kind of just want to show some process pictures of fabrication. This was a smaller wall, but on the left image, you can see the shorter units. It's hard to see, but they have a notch on that bottom, which those were placed kind of first, and then all these unique pieces that step down or up kind of were just placed along the side pretty easily. Kind of ran through quick, but it's kind of finished photo. Super easy install and quick process of fabrication once the building was already finished. And then there was a shorter one kind of on the back wall that we were able to use as a TV mount. I'm going to jump into the second one. This is a bigger feature wall project, really using similar kind of strategy of, a single profile of wood, but how that could change in dimension and dimensional length, and how we could arrange those along a pretty big wall. So our firm did not have we were not the architects of the full building. This is downtown Kansas City, but we were asked by the architects to fabricate a feature wall that spanned obviously this pretty large empty canvas in the lobby of this building. So I just want to walk through the steps of what we took their concept of and how we applied that to getting it to site and easily fabricated by others outside of our shop. So the architects just had this basic idea of this bottom left profile of a long piece of wood ash. And he came to us with kind of one profile that he wanted to repeat essentially along this full canvas, but we thought, no, that's too easy. We could make this a little more exciting. So we started thinking about how we could slightly manipulate the profile he gave us, really just in height, and then how would we start to arrange these units to fill our nearly 20-foot tall canvas on this wall that we had to fill. I don't believe there's anything truly random in the world. Even if it looks chaotic, there should be an order to it. And so we kind of tried to give order to this random arrangement of essentially wood sticks along this wall. But what we found was this kind of mathematical term called permutations, which was one way or one of several ways to create a variation, which one set of numbers can really be transformed to reach your goal. And we found that just using kind of 3 different lengths, you can see on the left, we would repeat the blue C length kind of twice to reach our full height. But then how could we kind of script something to help us study the random arrangement, but trying to find a goal within that randomness? I don't know if current students have gotten into Galapagos or the evolutionary solvers yet, but I haven't used it a ton professionally, but this instance was semi-useful to not say, here's my one random design and let's go with that. We wanted to kind of tell it to study hundreds of different variations of this and then choose kind of analyzing what was the kind of most space, which solution spread out similar units the most. Led us to kind of, this is just another GIF of that. By kind of reaching that design, it made us feel a little bit better about having a randomized kind of arrangement. But essentially then taking that arrangement into fabrication, how do we really produce, I think there was 600 different sticks of wood that needed to be produced, cleanly ordered, and then figuring out how we're going to mount these to the wall. So this number 3 up on the top right was, we'll see another detailed view of it, but we found consistent lines with our overlapping lengths. We found these consistent lines to have kind of these metal Z clips on the wall, which gave us, on the bottom, you can tell, regardless of the length of the wood unit, A, B, or C, there was a consistent dimension from the edge of each piece that we could mount a Z clip to, making it much easier for fabrication to kind of follow our key on the wall. So again, using parametric design to quickly output construction documents and as they change slightly once you get into fabrication has been super beneficial for our shop. Just another quick drawing of the different profiles, and then again, parametric design allowing us to quickly understand how many quantities of each different unit needed to be produced. So our shop could quickly cut down to scale from ash wood sticks, 76 for A, and then shape them up. So it was a pretty efficient kind of production line we created for it. This was the final design and kind of a key to help once we fabricated all these pieces, where each piece would actually go on the wall. Quick detail just showing those back kind of clips that would be attached to each unit, but once they were shipped on site, the construction crew really just had to follow our key and just place these on the wall. There was already somewhere to receive each one. So we used ash wood for this. It was a slightly lower cost wood, but gave us a nice kind of more white sheen to these. And you can still see grain, which is a nice texture to add to the wall. But again, just almost like Santa's workshop, just pumping out a bunch of similar units. You can see these all stacked before we sent them to finishing. And then once they were finished, we shipped them all inside to crates. And although this isn't pretty drawing, again, parametric design allowing us to quickly produce and output a key that for each row of these sticks, all the construction crew had to do was go grab that unit and place it on the wall, which was already received by Z clips that were placed correctly. So here's an install picture of that. Kind of interesting thing that happened was we got a call. They thought they had finished. They'd used all the pieces of wood, and they said they had like 3 feet left over, and that we were missing maybe 60 pieces of wood. And we were pretty confident about our script and kind of canvas that we knew we covered. And what we found was that they actually didn't space. There was a drawing in there that they did not space each of these rows out a 1/4 inch. So after they finished, they actually had to come back and re-space these out, which then kind of perfectly fit in the wall. You can kind of see these spacing on the top, but there's also a spacing between each as it moves from left to right. Next one is a more internal project we did at our office. And this was fairly earlier on when I got hired, and I was the first parametric or first employee with parametric skills that we could apply. So it did take me a minute to kind of get them to trust, the process, and especially with fabrication, the efficiencies that we could do. So this was a nice kind of test for that. So in our office, we had a pretty big empty space, and we're in an old warehouse that we've renovated with the fab shop in it as well, but there's just not a lot of private areas to go to. So thinking of how we could utilize this open space for kind of shroud in our office. And we had this idea that what it would create was this kind of mixing of kind of people and energy. And it really brought us to this idea of a nebula, which is the name of it. But a nebula is essentially this a star that has collapsed on itself and then explodes and creates many more particles around that start to interact with each other, creating a new kind of energy. So conceptually, that kind of formal looks at what a nebula is, kind of drove what we wanted to do. These were pretty early on pics, but it's evolved a lot since then. We'll see another picture later, but we did also, what kind of made us think of nebula was we had this large sphere that was designed as essentially to help plants grow inside. We had that kind of left over from an old project. We might as well use that to be a kind of focal point. So just going through the kind of process that we went through to see what kind of form we wanted and measuring kind of material that we could use and afford, since this was an internal project. But quick diagram just showing the basic setup. We knew our area, which was kind of driven by 3 circles that we just blended together to create the exterior. Spacing out all of our ribs that we knew we wanted, and then giving them different heights, kind of creating this, again, nebula-like void or shroud within the space. And then what needed to happen, because these went up to about 9 feet tall, they had to have different connection points within. So we studied quite a few variations of that pattern, but the one you see here is what we ended on. And we really kind of found pretty good fabrication efficiencies from that kind of joint pattern we ended on, which I'll explain in a second. But these were super simple and super quick studies to do once our base parameters were set up. Again, analyzing how much material and bend we could even allow for the ribs to be CNC cut. We just to prove that we knew it would work. We've also got a model shop in our office, which is super beneficial to test things out. So laser cutting all these pieces. Again, you can start to see some numbers and labels even on these very small pieces. And what we found was that, I don't know if you can see my mouse, but the joints are pretty repetitive vertically. If they're attached to 3 columns, then the next one directly below it is going to actually have the exact same shape. So numbering these actually became easier than what it was here. We just numbered everything from like 0 to 200, but we didn't need to. Each joint is specifically associated with its central column that it attaches to. So fortunately, these are a little blurry, but I think it gets the point across of, again, parametrically outputting all the pieces in order for us to fabricate, not only just having the number digitally, but having that CNC routed into each piece that was created. On the bottom, kind of gets to that joint repetition. Although we had maybe 200 joints, we really only had a single, much less cut patterns for each that just needed to be cut 3 times. So just getting into that kind of fabrication, and did a mock-up of this again to just kind of prove and get everyone comfortable with the whole process that we're trying to implement. So the mock-up was on our left. We didn't end up using it because we decided to change the top profile of these to be more rounded, just gives it that softer feel. But went super smoothly. There's no nails in this. It's a freestanding structure with just intersecting wood joints. Here you can just see the detail of the labeling of all the columns, and then any joint that needed to be attached was also labeled associated to the columns, so they weren't like different numbers or A, B, C with numerical. So I should have got some final, more recent pictures, but we had tried infilling it to make it a little more private with some small acoustical panels, but really now those are gone, and we've infilled this with tons of plants, which really is driven from that grow light being in the center. Next project, I think we're doing okay on time. Next project were these structures that were standing out in National Park in Arkansas called Hobbs State Park. So we were tasked with 2 different kind of projects. The one we're looking at here were trailheads for the mountain biking system at the main center of the Hobbs State Park. They wanted these just large structures to kind of welcome people and allow kind of gathering areas before maybe a group of bikers would take off. There's also, we'll see them in some pictures, but some campsite structures that you could hike into. You can't drive to them, you'd have to hike in. So it provides just a nice little element for your evening camping. But really just showing the breaking down of geometry. It's fairly quick, but honestly pretty simple. When I started with the project, somebody had designed these on kind of an ellipse rather than a true sphere, which we found pretty problematic for some of the intersections we were looking to get. So we had to take quite a few steps back, apply it to two spheres, and kind of work from there and see what we could come up with. Again, quick diagrams showing process of a parametric script, breaking things down and keeping things ordered with each row, knowing that if we're going to have, again, maybe 600 pieces of steel tube that need to be different lengths and different hole intersections, how do we keep them ordered? So I really don't know how somebody would do this without a scripting and having it parametrically driven. So again, since we're on a sphere, there's this interesting pattern of holes that might need to occur for each unit to connect to its upper and lower neighbor. So this was a mock-up we did, drawing, just trying to study that before we actually tried scripting it in, knowing there's probably a logical direction for us to look for these connections. So when that was applied to the full thing, you can see it's this top image shows all the holes for each different piece, and this kind of weird pattern that it outputs. And what we really needed was not a human to be cutting all these pieces, but a piece of technology that could really take a 2x2 beam. It's a hollow steel tube beam that would then be able to be rotated with with the machine and placing holes on top and bottom of each beam, as well as labeling each beam. So the image on the bottom shows you red is, maybe top, blue or bottom, but how varied they are per each different unique piece. More zoomed in profile of that, just one vertical section of one of these trailhead spheres. And we really just were able to take this. We found a fabricator in Kansas. They make trailer hitches for trucks. So they already have quite a bit of kind of digital metal technology and machines that we were able to utilize. So this machine really just took a very long 2x2 steel tube, cut it to its length, rotated that to put the top and bottom holes on it, and then spit it out and just kept going to the next one. So we found a pretty efficient process, because I don't think anybody would want to do this by hand. So then showing kind of the organization for our fabrication drawings. Once all the things were cut to length, how are we going to build this? We really knew we needed to build this in pieces in our shop before sending to the site in Arkansas, which is about 6 hours away from us. So doing this in pieces that they could just easily put in place with a forklift. Again, all those laid out. This is essentially the file we sent to the company that cut the beams. So some in-process pictures. It was a crazy amount of material, but everything was labeled and cleanly organized. So in our shop, we could easily stack these up and flex this into place. Although we learned, and I love doing the structural analysis of things, it's been hard for me to implement that kind of element into what we do here. But this was signed off by a structural engineer, so I didn't have to worry too much. Just had to trust that the process of everything coming together correctly, and it worked out. One detail was thinking we had to kind of come in and think how we were going to finish the edge of all these beams. Every beam needed it to sit on itself, so the beams that terminated at the ends really needed these smaller portions. And since these were kind of on a spherical shape, as they moved up, they needed to turn relative to that circle. And that angle is actually very hard to really tell somebody what it was. So it was easy for us to just cut out wood shims and tell them once they got to the edge pieces, these are your shims, and you could attach and tighten into the correct position as they moved upward. We chose not to finish the steel so it could rust and get this nice color, match and naturally blend with the environment as much as possible. Kind of keeping a more raw element to it. This is the smaller campsite structure. What I've shown so far is mainly those large trailheads for the mountain biking trail, and I think those large trailheads were about 24 feet wide by 16 to 18 feet tall. These campsite structures were much smaller. We actually did them first to make sure, the full process worked before getting too far into the big ones. Just a couple of details. The finished product. When you get below it, you can kind of start to see. We wanted to hide holes as much as possible, but it was difficult doing that. Just knowing how it needed to go together. So when they would put these together, they would always have a larger hole on bottom that allowed them to get a tool in their hand up and tighten all the pieces they needed. That's one of them sitting at a campsite. It's perfect dimension for you to also hang your hammock across the front if you wanted. And then again, we went back a while later to just see the evolution of rust and aging of this in its natural place. And got one more I want to share, the last one. This was a we were commissioned to do an art piece that was in a building. We were not the architects of the building, but again, we're commissioned to do an install piece, and this was called The Sounds of Earth.
So really, Josh,
yeah.
we've been to be
we
fast.
can,
yeah.
I can be done if you want.
No, please show. It looks really nice, but
yeah, I'll go quick. So the building was based off a concept of reverb, which is sound, and we took that into consideration for what we wanted to carve. There was on Voyager 1 a golden record sent out into space that contained 21 tracks of Earth life, like nature and human life. So essentially, we took and recorded those 21 tracks and wanted to map them onto a canvas. So really, after recording them, we would get the sound waves and be able to kind of manipulate that into making our artwork. So each track was a different length, and as we ordered them on the canvas, kind of would just give different effects. Just kind of studying that and mapping it into our constraint of thickness of wood. So we studied a lot of different ways we wanted to produce this texture, and kind of ended on getting into actually carving it with a CNC router, choosing a bit that represented kind of just what a record would be played on, a triangular bit. So as we mapped it in and started kind of blending more and more curves between them all, just coming out with this kind of nice textured finish that represented all these tracks blending together. We were able to study the different types of wood or material we wanted to use, and just ending on these different studies. We also used reclaimed wood, 21 pieces to represent 21 tracks that we used to kind of get the final guy. It just came out with some nice texture and movement across the whole thing. That's it for me.
Thank you very much, Josh. really impressive, very artistic playground you have. A lot of space, and it looks like the office you are. It looks nice. It's very, very nice, no? The ambient, the feedback with the workshop. No, it's very nice to have that.
Yeah, it's pretty rare collaboration, so it's fortunate to find it and be in the hometown as well.
Great. And how much of your time you spend like in strictly on parametric stuff?
I want to say about half the time now.
Okay. Is it increasing?
Definitely increasing. I mean, there's always those lulls of time, but we implement it a lot. Yeah.
Very good. Anyone has a question, or we move forward? Yeah. Okay. Let's continue because we have a long session. Please, Giacomo.
Hi everyone.
Hi.
Joshua, good job. Very good stuff. So I didn't improve my English from my last time in the master. So it is what it is. Let me show the presentation. Can you see the presentation?
Indeed.
So a short presentation about where I ended after my master. I'm working Remond, that is basically a general contractor that takes care of each phases of the construction, starting from the design, passing through coordination, finish with the delivery of the finished work. So one of the very first, the first project where I was involved, when I come here, was a dome of Alwas Plaza in Dubai for Expo 2020. This is a very interesting project, because in this project we touch a lot of topics that we saw in our master, like from finding minimal surface, structural optimization, digital fabrication. Is a lot of stuff. So this is the I don't know if anyone know this project. I think so, but this is the dome. Here we have some number about the dimension, 130 meters of diameter, height about 67.5 meters, and something around 14 kilometers of beam, steel beam. In this project was very important the workflow of information of data. We have a lot of data coming in and a lot of data that we have to send out to the construction and to the designers. And in this case, the important thing is that we work in this project also in the construction phases. So we have to merge the design criteria with fabrication criteria in order to have a central model, 3D model, wireframe, that is basically the generator for all the design, structural and installation, both. Here we can see how many in field are influenced by one central model, that is basically this. All that project start with this. At the beginning, at the very beginning, we had a bunch of 2D documentation and 3D model, partial 3D model. So what we did was to merge, found a way to merge all that information in one file that was entirely managed in Grasshopper. All the information comes from Grasshopper. So we have to start with ranked 2D files that we can see here to the right. That is basically a top view projection of the dome that we had to remap in a 3D geometry. That is this, the profile. Remap all the 2D dimension information in this 3D model, and then like unfold the entire geometry in a 2D dimension in order to be able to speak with construction team and the designer, and be able to how to say bring each item of the dome in the exactly 3D position in space. The dome obviously is not a perfect sphere, is a little bit more of a sphere that is bring more complexity of the geometry. This is an example of what kind of information we have to extrapolate from this 3D model, like structural information, installation devices, all from Grasshopper. The second problem that we had to resolve was obviously the geometry that was wrong, like this, especially in the contact part of each panel. Let me call each ring and form panels. So in the contact point of each panel, we have this issue. I mean, each panel has to be tangent to each other in order to be constructible. In fact, in the right, we can see the a model, a mock-up, the very first mock-up that they did in Dubai, where, fun fact, they saw the problem, the geometrical problem, and they resolved, but they didn't say nothing to anyone. So when we have to build to produce the construction documentation, we saw a lot of this kind of problem.
How did you solve it? Are you going to show?
I will show you in this way. We run a little script, a short script, simple script that that basically keep tangent each node, contact node, and try to fit the panel with the minimum angle deviation from planarity. All this stuff is for basically is for the pre-construction process. I mean, our main focus was the workflow information from our model and construction team and designer team, because a clear and simple workflow of information is traduced in time and cost saving, basically, during construction. So all the process that we not the process, all what we did in this project was basically reconstruct the entire structure in order to avoid this kind of problem in the construction phases. So here we can see the different position from the starting geometry and our geometry after optimization. This is an example for typical arch, the first geometry, and how we solved, maintain each point of contact with each panel tangent. And working with very minimum, how can I say, error. I mean, we had something like 1 millimeter of tolerance, 1 millimeter and 2 of tolerance. I mean, for example, big structures apart, we have this kind of items that this is like a CCTV camera, security camera. We had what we did is taking in consideration the deformation of steel to build this item. We have to consider the welded proposal and the folded one, in order to avoid this kind of clashes. After our optimization, the result is this. The white panel are the unchanged, and the black ones are the modified one. This is why because sorry, this is because for example, the white ones are the only one with one curvature. I mean, it's a ring composed by several rings, but with only one curvature in horizontal plane, with the center in the same axis, the same plane, horizontal plane. And the black one are the double curvatures one. For example, this one at the top of the dome was the animation one, the animated one. Do you remember? So this is the result visualization from the final geometry. They changed it that we had from the beginning at the end. The red one obviously are the bigger. Also, we have to deal with minimal surface. I mean, in each panel, each ring, there is a membrane, elastic membrane, that is not mounted in a plain ring. It's obviously mounted in a double curved ring. So what we did also here was to find a wireframe for the membrane, and then run a script like Kangaroo to obtain the minimal surface of this ring, that have to be. I lost one slide. Basically, in this project like this, we have a lot of how do you say, limits, restriction. We worked with minimum tolerance. In this case, for example, we have to, this ring where the minimum surface of the membrane is fixed is not planar, like I said, and he have basically this is a three arch with how do you say, kinky node?
Yes.
Perfect. That have to be less of 3 degrees. I mean, this ring is composed by 3 arches that have a kinked joint with maximum 3 degrees of tolerance. About what I was saying before, the workflow is very important in order to saving time and money during construction phases with a complex construction process, pre-construction process, where we in digital we can see what we are doing basically. This is an example of what we did in our office, what we obtained in Dubai. Pretty much the same thing. This is some. I don't know if I can show you these images, but I don't care. So it's very interesting how they construct all this. How is identically of what we did in Grasshopper. Obviously, all the process, construction, design and construction process was focused also in this topic. I mean, transportation, modularity and transportation for Dubai, because all this was built in Italy. Another fun fact is during the how do you say, during the lifting
yeah, direction.
Yeah. The elevation of the last ring, one of these hydraulic jacket was broken. So they have to the team in Dubai has to run a little simulation, short simulation with Caramba to redistribute the hydraulic jacket to lift the last ring. I mean, 1 second, the last one. Grasshopper was used also for to do this kind of stuff. I mean, 4D, 5D. We use the model with Grasshopper for each phases. And this is a project where we only, I mean, we didn't design the dome. This is the last ring that where they has to redistribute this element in order to lift the last ring, and they did it with Caramba to find the right position. And the final result is this. Another short project that I want to show you is this is a project that we did like design and construction in all the phases. But in this case, Grasshopper was used only for the facade construction, because who designed the facade had no idea how to build it. So we use Grasshopper like tools in order to, first of all, define a good pattern of our facade, and second, to take control of this facade, because what we didn't have at that time, it was control about what we designed. So talking with the constructor, we had a lot, like in the first example, we had a lot of dimensional limit. So what we did It's basically take control of what we are designing, study the pattern and the how do you say la factibilità?
Feasibility.
Exactly. Because in case like this, the constructor will say to you, I can't build this. It's too difficult. It's impossible. The panel is not planar. The facade is too, and you can say no. I will show you it's possible, and I will show you how. So basically, it's what happened here with this project. We study and define all the anchoration point at the main structure of the facade, and then communicated with the constructor to build what we want as we want. And that's
Great.
it.
Very good, Giacomo.
Thank you.
Geometry to help.
Exactly.
I am very impressed by the size of your dome. I never had like the real scale. I thought it was big, but not so large. I mean, yeah, I guess like yeah, like a couple of tones, no, like 5 tones each piece, or how much is weighting every piece?
I don't remember, but
It's huge, yeah.
Consideration that is this is like the thinner part of the dome.
And were you stressed in the assembly? So
What?
were you if you were stressed, I mean,
Yes.
when they were assembling it, okay, a long time, no? Stressed.
No.
No. Very nice.
Very nice job. Thank you. I have a lot of things, a lot of material about the dome. We can do a masterclass.
Yeah.
With Grasshopper and this dome.
I imagine. No, I'm very happy. I mean, Josh is was sharing project where use the tool as a pure factory of designs, no proposals, and here it's more about making it done, or like mainly the rationalization of it and making it buildable. So I think it's very nice.
Yeah, of course.
And making a lot of like custom tools to visualize and.
In fact, in this project in the dome, we had. Let me show something very quickly. We had. I mean, at the beginning, were less parts and more simple. After our optimization, we have more parts with a little bit more of complexity, but now is working. I mean, the geometry was wrong. I mean,
yeah.
For example, in this case, they want a like panel with one unique radius. How you can see here. I don't know if you can see.
Yeah.
After our optimization, we have 3 radius, different radius. But in this way, is constructible. So that's it.
Yeah, very nice, Giacomo. Thank you very much for sharing it.
Thank you.
Okay. Who's next?
Me?
Hi, Adrià.
Hi. Hello.
Hi.
Let's try.
How are you doing? You are very far away from the camera. You're in a very large room, no?
Yes, in one of the conference video call rooms that we have, meeting rooms. In the
Great.
Yeah, let's try to show.
Are you in Olot?
Yes.
Okay. Okay.
Share it and here. You see the screen and everything.
Yes.
Oh.
Very large conference room and very large typography.
Yes. Okay, I will show you 3 projects, well, 3.5 maybe, and I will. Okay. First of all, I will present myself. I'm the master at the first edition, as you said, in 2016-17, and now I work in Belapart, and I am teaching parametric geometry in UPC architecture bachelor at 4th grade, teaching grasshopper geometry with grasshopper, and I do some 3D models as freelance. Well, now I'm working in Belapart, that will present most of the projects, but the first one, that it's a company that has more than 80 years and 78 employees, and we have done some beautiful projects, specialized in glass and steel construction. We are constructors. We would be the company, the constructors that Giacomo would hire to build so it's the next phase. I work in the next phase after Giacomo, but some kind of sadly, most of the projects I have participated, the main constructor that didn't have a Giacomo, so I had to absorb that job too. So it would have been nice to have a Giacomo that could solve all the problems before they arrive here, and we had to solve them and discuss a lot with the architects and everyone. And it's okay. Here are some projects that you can check in the website that they were done before. But as I said, it's mostly skylights. I represent one skylight, facades, special facades for retail, moving facades, and high glass with more than 6 meters panels. Okay, the first project, I did it by myself. It's as a freelance. It's for an architect office in Barcelona. It's Pica Aguilera Architects, and it's these panels of this facade that they wanted to make some freeform panels, and it's a freeform geometry. They didn't know how to do it, and then we worked with Cemex and Kinetica that they built the panel. I think in Kinetica there is someone that already made the master, and well, in these panels I could able to play a little bit, and it's the first job that I was hired to do something with what I learned in the master. I used grasshopper and kangaroo. Maybe kangaroo was not. I didn't have to, but I just wanted to play somehow, and they paid, so it's fine. And this was the panel. It's made of 2 kinds of concretes, and the project was to make this concrete panel that it has some 3D shape, that it has this part that it was like inflated, like simulating dunes, that when the sun is very high, it gets shadow to itself because it's in Mexico, and it gets not as hot as in winter that the sun is low and will touch all the surface of the panel with no shadows. So this panel makes shadows over itself, and that was the idea of this project of these panels. This was the intent design, or what they gave me. As you can see, they couldn't make this 3D shape, and they has a lot of problems. So I had to solve how to build this and how to design this panel to make it so they are able to fabricate it. This was my input. I couldn't. I had to fit into this size, into these measures, and it was just 2 panels that combined in certain way. You see that random facade. So with the architect, we agreed to these lines, artistic lines that he liked, and everything that is over these lines had to be like inflated, let's go outside of the planarity, and what is inside of this curve should be planar. So after discussing with, as you can see here, these things. Okay, so they cast shadow to itself. After discussing with the architect, we have to agree to this curve, and I delivered this and the 3D models. and the geometry points, the center of gravity, so they can calculate all the structure and everything. So it's not just about the design, you have to give them some properties of the pieces so they can work and build it. I will explain how I did it. It's just with Kangaroo because it was the thing most similar to the master that I did, so I explained all the process. I had these two panels, and I made these zones that are the planar ones, and the not planar, this outside zone. How did I did it? With Kangaroo, I took all these points, and I made like catenaries, so I could I draw them here and elevate all the points to make this nice curve with some elevated points. No? As we can see here in a zoom, all this line was elevated going up in the top of the edge and then going down to cast shadows here. The point that was with most distance to the edge of the panel is the point that it's higher, so it has to cast more shadow than this one that it's nearer, so it casts less shadow. Okay, next step, doing all these strings. The strategy was doing a lot of strings, no? And then I will pull these strings in this chord, in this edge, to elevate them. To make it nice, I could not just take them, so I divided the thing into set of points. The normal strings, all vertical, and this string here, the edge that we saw before, that had elevated points, and their partners, or their adjacent points, had to be perpendicular to the curve to have a nice effect of convex or concavity. If not, it doesn't work as well. I prepared all of this like if it was a funicular shell. That was my final thesis in the master, so I just wanted to apply it somewhere, and it just worked for this design, so I did it. So I divided the points with the points that has normal strings and the points with the string that has the curve. I meshed them together, and then you make the mesh, the ordinary mesh, you clean it with Grasshopper, everything, and we can see here the mesh in 3D, how these strings on the mesh had this top edge and goes down. What comes next? With Kangaroo, we have all these points here would go with a gravity zone going down, and all these points here will have gravity going up, and as they are more near to this edge, the gravity force that goes up will be higher exponentially to the points that are farther to this edge. And well, all the strings, all the edges, inside edges will trying to have the minimal surface, so it's not loose. So it will have, this string will have some strength to keep it planar. So we have this, and after the Kangaroo, okay, we have to separate the anchors, all the perimeter edges, the curved edge that we want to keep. Then we have these points that with the gravity, and all these points with the gravity that goes upwards. So at the end, we have this panel that is like inflated here, but here it's flat, or almost, and this is concave, and here it's convex. And here's the topography of this panel that casts shadows to itself. With this, we send it to the Kinetic and CEMEX, and they produce the prototype that would be this panel. They saw some mistakes in the design of their input, so we have to make it thicker and a little bit more thicker. And we had some water problems, so we made this adjustment to the design. Thanks that it was with Grasshopper, it was just changing a little bit the inputs, the thickness and everything of the design, play Kangaroo again, and have the final result with here the topography map of both panels. For example, we make all the changes, and then we had these two models of these two panels. This is the outer face. The inner face is just a normal surface that it's not big deal. So with Kangaroo, we could design this nice effect of dunes and being very smooth and everything. And here's the composition of the facade, how could it be, so the architect could approve it. Well, we made like 6 or 8 versions until he approves. Usually we work with the architects, or I like to work with the architects. I go there and let's make a lot of iterations so until they approve. So it's nice to work with Grasshopper because you can make a lot of changes every time you go to the meeting with them and they like or not like what you're doing. And well, this is the final panel that will go to the building, that has gone to the building in the factory in Mexico. I think it's Kinetica. And here is the panel already in the facade of these panels. As you see, it's just these two panels. And here would be the whole building, the facade, with all the panels already installed in the facade. Something important that I learned in this project, before working, always ask to the company that will fabricate which software they have, because I designed everything with Kangaroo, with a mesh, because we in the master played with meshes and everything. And when I delivered the mesh to them, they said, "Oh, we cannot. Our program does not work with mesh. We need a solid." So I had to repeat everything and try to make a lot of sections and rebuild it to make it in a format, in step or eases or whatever they needed, that it could not be a mesh, a BREP, it had to be a BREP, so that they could work with it. So now I always ask that before working. So it's like, what will you open? Okay, then we can work with it. So this would be the first project that I did, just these panels. Okay, as myself. This one, it's done in beta part. In beta part, what I do is I'm in the estimating team. So what I do is just price the projects, study the projects, and check how they should be built and make the offers. And when we win, the engineers design engineers and manufacturers, we have a workshop, will make them. Until there is a project with complex geometry or they have 3D models, and then I go to that team and work with them. So I just have 3 projects that I can show, 2.5 projects that I can show, and they are very. This one is very focused in construction, how to details and how to construct it. It's this facade here of this kiosk in a plaza in a square, in a London Exchange Square. Okay, I did Rhino with Grasshopper and SolidWorks because all the engineers in the facility here in our workshop work with SolidWorks. So I had to coordinate the 3D model with SolidWorks and Rhino, and every time go back and forward. So this facade, it's here in Londres, very near to this important place. So it's an important extension, and we had this curve that is the render from the architect that he had this curve that he loved, this curve. So you can see here, all this black part is our scope or the part that we did from the project. What happened? Well, they didn't do any 3D model, and even though it had this curve facade and it goes changing the heights, so without working with 3D, it was impossible to do anything or for them to understand what they are doing. So our inputs were the structure done by Arup and some 2D drawings, and these 2D drawings. So we had to make all these panels. My job was to make all these pink panels here that are the metal panels, and to create the geometry that could be buildable. And here was the input that I had to make, and somehow working with these 2 points, knowing their height, how this model should be, because they just give us the numerical inputs and the curve. And actually, this curve was wrong because I don't know if you can see here, but the panels between them, the curve, were not tangent to each other, and so it could not be buildable. And these theoretically perpendicular fins were not perpendicular to the curve, so you could not build the glass with the mullion being perpendicular to the curve. So we had my first job was to change this curve to a curve that could be built. And well, here we have some more inputs. This should be perpendicular to the structure, to the glass and everything. And here we had this U that, well, it's a ruled surface with curve, 3D curve, because it goes higher, changing the topography, and it's just curve. And we see here that something has a slope, something has not, so it has very challenging in geometry-wise. Here is the input, and we had to correct all these curves to make it tangent to each other, and discuss with the architect why his curve was so nice and that he wouldn't change anything, and we agreed to just change it like less than 6 millimeters, and he always had he cried in the meeting almost because he didn't wanted to change the 6 millimeters of this curve. So we changed it and we regularize it, and we put all the fins perpendicular to the facade so it could be buildable. That was my job. Here it's make it again. No one could see the difference, so it was okay. And all of them are perpendicular, and now we could build it. What we did is with this input in a 2D drawing under heights, we could do this. I did this surface model just for everyone to know where they should be and what should be their axis and exterior surface of their elements. And then they could work all with this coordination model that I sent to the architects. The architects sent them back to me because they didn't know how to open it. And I just had to coordinate, as Giacomo did, that they did in Remond with the main constructor didn't have anyone with 3D knowledge to coordinate the 3D model. So it was my job to coordinate with the structure model, the concrete model of the park, and the topography model to make that everything works fine. And this was the model. And then the job in Grasshopper was to we always go in a rush. Like for next week, you have to already be building it. So we have to create a parametric model that what it did was to every one of these panels, first thing, enroll them with giving their numbers. And second thing, going from these panels to all the superstructure to hold the panels. You can see here, this was my input, take one panel and create these elements. You will see later, like these joints between them, and how to hang these panels and making this tolerance space between them. Here's the whole panel with all the structure, and this is it. This is a 3D model of the panel and all the superstructure it has behind. So what was good with Grasshopper, I could input all these panels at once, and just working with one of them, there were like 39 panels. In just one day, we could have all the panels ready to be sent to our supplier. Someone is writing something? Well, to our supplier, and here would be the model and this upper part too. And we had like two options. So Grasshopper could decide if this solution fit or didn't fit in this space, and we had option A or option B. So it was really easy and fast to do. And, well, easy. It was not easy to prepare one, but then it was easy to adapt to prepare 40 of them and make them pretty fast instead of one by one. And here with Grasshopper, we could do check for collisions with other parts of the structure. And for example, here with Grasshopper, we could check collisions and tell it to prepare these spaces here to subtract all geometry so everything could fix perfect to the other ones. Here is what we sent to the supplier, and here you can see one of the platforms. This one green, how everything is called. So, I mean, it's very constructive how to make all this superstructure to hold these panels really quick and with a systematic. Right. And this is another kind of panels that where I had to do this pattern of holes adapted to all of the different dimensions of the panels. And here is how we are in our workshop, preparing the panels and assembling them here before going to site. Here is the panel assembled, and here is a prototype that we did to check everything and to make all the changes that we need. And here is they are painting the structure with a new technique of being black, like ash. Well, and here are some installation pictures. This is what we received. We go with the topograph, make the survey, prepare everything, check that everything is fine, because every piece is designed at the millimeters, so we have to check that everything, once it's installed, it's according to our 3D drawing. And I had to verify every piece, every element with Grasshopper. It's really easy to make topography and survey verification. So it's really, really useful for that too. Here we can see the panels once installed and before installation, and here all the substructure already in place. And here they install the panels and some panels already installed between, and everything fit nicely. It was really surprising that everything fit with that geometry. Here, well, some images of everything fitting, how they made these panels with the holes. And here the final project. The detail with the lining here inside, this 10 millimeters that the architect wanted to have everywhere. This is the project with the glass facade and this S with this light, and at night, well, this is the station, the final one. Okay, this other project is in Barcelona. It's a skylight. I use Rhino, Grasshopper, SolidWorks to coordinate with the other members of the team, Cloud Compare and SolidCam, because in here I did the notes, and with 5-axis machine, and that I will show later. It's here in Barcelona, in the MUBA, in the Museum of History of Barcelona. We had this input. I think it's made in a SketchUp, and it was useless, very bad. And the axis, but we had like, here's your project. In 1 week, you should be buying the materials and start producing, because they had already the party, the finished party in November. We started in July, and it was like, it has to be done for that day. It's the party, so next week I start building. So we could not correct anything, and we had to have exactly the geometry that they gave us. Although I thought we should have revise it and make it better. All of you would have make it better. It's like a kid pulling up points, actually. Here's the geometry, and all these points have different heights with really no sense. Oh, and this is not a square, so every node, everything is unique, which was fine and stressful at the same time. Here's the geometry that we made, the class, all the nodes, as you see here, in different color, and all of them were different. And the perimeter nodes, 8 bars node, 6 bars, or 4 bars node. Something else that we did here, was with Galapagos. I ran an optimization of which was because they did it with conceptual design, like this square, but they didn't take any topography of the zone. So when we had a point cloud of a 3D survey, I had to make where this skylight should be optimized to have the same or the most regular space between the skylight and the actual real wall from this historical building. So with Galapagos, we ran optimization to check which was the angle that we should put this skylight to fit the best for the gutter to have a gutter here. And here you have the real wall is in a point cloud, how this was more or less inside the hole, the theoretical hole. And it fits nicely, and we knew exactly all the measures everywhere for the skylight. Here is the gutter that I was talking about with this distance, everything fitted. And here's the detail. I'm saying before, this should be symmetrical. So every bar had to be perpendicular, or had to have the axis in the bisector, with the same angle at each side of the panel. So if the panels were not regularized and nobody with a little bit of 3D knowledge did it, and it's what happened, every panel had its own angles and normals. So, well, it was chaotic, and every bar had its unique axis slope. Another thing that it's really helpful in Grasshopper, how to do the packaging and how the skylight, where to split it to go and build it later. So with Grasshopper, we could fastly check where to cut this skylight to pre-assemble in our factory, in our workshop, and then move forward. And here are all the slopes of the classes and a quick analysis with Grasshopper. It's really easy to do this kind of analysis of geometrical analysis. And you can see everything is different. I don't know why. And the angles, you could guess or expect that everyone would be like this, because it's like a sphere, if you want to. It's convex. It should be convex, a skylight. But no, somehow one of them was like this, was concave, which made no sense, but they didn't allow us to correct it. So I had to play with that, and that's all. And you can see the perimeter bars, that every bar had its own slope too, which was very fun, because not even these edges had the same slope, which was difficult for the nodes, for machining the nodes. There is one node coming from Grasshopper with all these holes. Here we had another hole, and this in red, it's the stock we would buy of steel before machining. Here it's in solid cam. We then use Rhino cam. We have solid cam to do the machining. Here we see all our tools. Here another kind of node with its stock, original stock, and all of this will be out with the milling machine.
So it's a solid block?
Yeah. All of this is a solid block.
It's not okay. The joint is not hollow.
Not hollow. Which one?
No, that one. The joint is not hollow. It's solid.
No. It's solid. Inside it's solid. We just have this small hole here, so we can weld it. Because if it's solid at the faces, in the faces, in the adjacent faces, you cannot weld it to the bars. That the bars are not solid. So after this hole, we did a simulation of the milling machine. Here you see this would be, and we could start taking out of the machine, and here's all the operations of the milling machine, the 5-axis milling machine. And here is the final simulation, how it could be, and here the name of this node, the B, C, face B and C, because it's a corner, number 4. Well. And here is the node inside the machine after the machine finished milling it. And here is the name A1. This is the A1 node. And as you can see, it's solid. There's something inside. But some nodes, we do this hole here goes through all the node and has here in the middle another hole to put some cables inside the structure. As you can see here, you have these holes, and the cable goes inside, and it could cross all the structure.
Sounds like super cheap, Adrià.
Yeah, super cheap. It was not expensive. A lot of time in the machine, a lot of steel, but the fit was perfect. And when we installed it, it had 2 millimeters of error in one diagonal, and you cannot see the nodes. The finishing is amazing. Oh, you can see here the tubes. Well, doing this, you can see that everything fits perfect, and you cannot see. Well, here's the paint, but you could not see the joints in the welding parts. These ones had not to be welded. I mean, with Grasshopper, what we did is to check. This one was with nails, screws here, but some of them, the welding ones, was like this. It's not all welded because the welding machine cannot fit between these two holes. I mean, if you have to weld this, you cannot fit the welding machine here. So there are some welding parts. So this is why these two are so long, and this is so short because it's screwed, and we then use the welding machine, so we could weld here and weld everywhere. As you see here, this can be welded, this cannot be welded unless the node is like this, and that is way more expensive, like 8 times. Here you can see all in our workshop with all these templates that were made with Grasshopper 2 to check the height of everything and make the templates to prepare the structure. Here is the structure, how we were preparing it. Here is me checking the node that everything fits fine with the templates. And here you can more or less see how the bar goes changing its slope. And it's the node who had ruled surface from end to end to absorb this torsion between bars. So every bar could have the perfect slope with the class. That was the difficult part, to make all these nodes to all fit the perfect plane of every triangle. And here it's already we divided in 3 parts at the end, and we fit it here. It's in the hole, everybody fits perfect, everything. Here is the node that you can see that this one you can see a little bit, but here you see nothing. So it's expensive, yes, but it looks perfect. You can see some structures made in Germany or somewhere else, and it's horrible, the nodes. And here it's perfect nodes that you see. They wanted to see nothing, so you could not identify the nodes. So we said, okay, machining and welding as much as we can. And from the bottom, you can see nothing. Okay. See, this is the final result. It's here, and it's this one. No, you can see it here. And here it's from outside, how it looks. And I don't know how I am with time. I have one more or less project. It's classified. I have to ask if
it's classified, yeah, you have to show it.
What?
If it's classified, you have to show it very quickly.
I can show it quickly.
We like secret things.
Yeah, it's just a specific part, so you cannot see the whole project. It's when it's finished, it would be nice to make a presentation, but now just a few points. And if you could, you are recording it. If you publish somewhere the record, cut this part, it will be fine.
Okay.
Okay, promise. But I want to show it, and it's very cool. Okay, it is specified. I cannot say the name of the project and not where it is. It's similar to Giacomo's. It's a tube structure in a preformed 3D shape. And it's here. It's like a torus. And I'm here with the building. It's inside another building.
Wow, it's beautiful.
And it's all made of glass. 3D
doubly curved glass?
Doubly curved. Yeah, this is a torus made of, this axis was an arch. So just, and this one is an arch. But from here to here, it's a clotoid. It's clotoid, it's an ellipse, no, a spiral with always changing the same time the same normals, and changing the radius the same, always a specific change. So it goes from torus, this spiral, to a cylinder that is with a slope. And on the other side, in the other axis, we have the same. In the middle, it's an arch of a circle. Here, a spiral, and here it's flat. So we have a torus, something unique, special 3D, to double curvature, unique double curvature, flat. So it was crazy as a geometry. And you can see here all the shapes. And this is the catch against the existing building. And it's here, and the glass was head strengthened, not annealed, which is a new technique that the glass suppliers developed. Was the first or second time that they tried it, was for this building, and it had a serigraphy pattern, and the structure goes like this with spirals that are not geodesic, so they have torsion. They have, well, I mean, the structure was crazy. We'll see some parts. This is the prototype that we did to make sure that what we were doing was fine. And I will try to explain. As you see here, this is a structure with the three bent tubes with torsion. These plates with 3D bending and torsion that we find a supplier that could make it. And then these bars are flat from one node to another, joining all the spirals. Here is our proposal. You see these spirals, the 3D spirals that went free inside the surface. So the consultant engineers tried to correct it, we said that we had a better place, a better thing that was corrected, but making these joints where the joints are. So we had these nodes, 3D machined nodes in a 5-axis machine to join the 3 pieces, the flat and the curved one. And they said, okay, let's make one radius and to simplify it. And we somehow were like, we are too cool to simplify anything. We'll do exactly the geometry the architect wanted. And we were into that to make the 3D exact shape that the architect wanted in these spirals in this 3 freeform with double curvature shape. So we had these tubes, here are planar, and I did a 3D in a grasshopper. I make how to create all these nodes adapted to everywhere. So you see here the node, an easy one. When these bars are like this, how the node, the field, the solid one, it gets high, and when the solid one gets higher, when this angle is even bigger. The smallest one, I think it was 24 kilos. The biggest one, it was like 45 kilograms of steel, the final piece. And here we see these nodes, everyone with its own name. Spiral 15, node number 2, spiral 15, number 3, and every node, every time getting higher. And here how we have the normals to the surface, the normals to the spiral, and how we had to choose every time which axis, which vectors to work with for every element of this node and structure. It was very complex geometrically. I mean, there's no optimization or anything, just how to make exactly that free-form random shape that somebody wanted and how to make it feasible. Yeah. Here you can see the node in red, how we connected to these tubes, and how these tubes had this small window here, so you can put the hand and screw all the screws to the node. And here could be the flat ones. Oh, you see here that every time this angle was different and this was different, and we have here a union point that was normal to the surface, and these bars with torsion where the glass was supported and symmetrically to each part. And we had every bar supported to the node, the strong one, and then we had some points every, I think, 400 millimeters. We had one support to the tube that were rotating inside the tube, because the tube was not geodesic, so the holes had to be normal to the surface, and they went randomly inside the tube. So that was fun. Here are all the kinds of nodes. At the end, there were 188 different nodes. 144 was this kind. That was what we called a standard, because even though they keep growing, they were a standard. Every one of them. This one here, these two, weighed like 150 kilos. And that was crazy. In the milling machine, we had to move it 5 times. It was crazy for the one who did the milling machine here. I did it in the MOVA. I did some milling programs with SolidCAM. Here, I didn't. I helped to think of how to do them, but I never touched the program. And here we can see how we milled. We come from this cube. This was a prototype. We milled one face. We rotate the tube. Then it's a 5-axis machine. Here we rotate. We kill the other face. Here it's making all the finishings, and here's the final node. So we go from this box. I made the optimization of which could be the minimal box for every node to make it personalized, to have to buy the less steel possible to create all the nodes. And here is this is the example of a steel one. It's here, and here it's one of the big ones. Here are some of the big. Oh, and we created this in a 3D printed to check if it fit in the machine or not, how to hold it, and where to put all the holes, if the machine could reach that point or not. So we had this testing part, and I have this here. I don't know if you will see this one. Let me see. It is the final touch. Well, okay, this is, if you wanted to watch the milling machine, how it works. For example, this node was like, I think, 14 hours to make. So yeah, we were from June to October making nodes non-stop in the milling machine. Okay, this was the tubes to make the structure. And here is the top part of the structure, how we assemble it, how we tested that everything fits, how we simulated the glass here with this waffle that I prepared to check that everything was fine and all the tolerances were okay. And having these 3D machined nodes was perfect because if they fit, they fit, and everything was perfect. If not, welding it would have been crazy. But having milling machines at the millimeter and checking all of them, it made the job of assembling it very easy. Here we could check in the 3D model all the everything was in place. Oh, and we had these special nodes that had to adjust to someone's structure that was here, but we could just facilitate that it should be moved. I mean, other structure could move in a way, their structure could move in another way. So how to put these rotating points in which plane, in which axis should it rotate, how to have these planes. It was very fun to prepare this, because we have to coordinate with the 3D one here that they send me like, we have this, do as you can. And I had to prepare all how to make this mass with our structural engineers to check that they made sense for them. They made geometrical sense and everything. And we can see here all the tubes, the spirals and the flat ones, and these connection nodes that I showed before. And this here, before they put the flat bars with torsion. No, here will be a detail in render. This goes to weld it, to screw it, and these points. Something to optimize in Galapagos too. Here will go the glass, and the glass had to have with some screws. Here we don't have anything to put the screws, so we had to check which would be the perfect optimization to place all the screws, but avoiding these holes here. So we had to check how to do that. Here is welding parts. We tested one of the spirals. We built it inside. We checked everything was perfect. With a laser scanner, we checked all of the tubes if they had any deformation. We checked all the nodes with a laser scanner to check if there was something wrong with them. As we checked that every piece but one tube were perfect with just 0.2 millimeters of error, and we checked that one spiral was good, we said, okay, everything is good, let's go. And we went with all the elements to the side. Here is what I was saying. Okay, this is the spiral with the structure with these covers, and here is just silicon between glasses. And
sorry, Adrià. So can you go one back? So do you laser scan that on site, or you just?
No. Here in the welding, somebody came and they scanned all these tubes. Every one of them, there are like 180 or so. All the tubes, they scan them all. Yeah, with a
just to verify the construction and the whole and the image on the left. Did you check that geometry in space?
This one. No, we have these templates here.
Okay.
And it should fit.
They were matching. Okay.
And the last template that I prepared in Grasshopper. So if it fit all the templates, it's okay. All the tubes were perfect. All the nodes were perfect because we checked with an arm. So if it fits one, we said, okay, if one fits and everything is perfect, it should be perfect. So,
the way to go.
Yeah, we're good to go. Let's go. Here is a detail of how we finished at the bottom of the building with this special node that we saw before, how it reached a planar space. And here's the upper part, how it fits with this corner, this node here that it's 50 millimeters. And this here that it's like a cone, but elliptical cone. It's very difficult to build. And it was not, we made it easy at the end and cheap, but when we asked how to bend this in some steel supplier, bending supplier, they said it was over expensive, that we would be scared of the price, so we go for somewhere else. Here is the top of the building, how this sphere closed, and here there will be some windows. So the cables there will be some cables that should go here, over here. And here's how we go with the cables, with this other tube that goes alongside this big tube, and between the tube and this planar this planar, this with torsion plate. And I mean, geometrically, it's so fun and it's really amazing how to create all of this. And here is how the tubes, the cables arrive here, go to this channel, and can open all these windows and the lights. Here are the windows. And how the water will go from here, go into the channel to outside. And well, this is a cool part. This is serigraphy. They wanted the building to have a fitting pattern from.
Okay, now we know it's in France.
Yeah, or Monaco or Luxembourg.
Yeah, Belgium or Canada.
Yeah, and we can go from 10% to 100% of serigraphy, and they supply us a pattern. I said, this pattern is very difficult. I said, you know Grasshopper, you should know how to do it. I said, yes, do it yourself if it's your job. And they said, no, you know Grasshopper, you do it. And at the end, I had to create this pattern somehow.
Come on, it's nice. It's a nice job.
Yeah. If we did it with Python, I will. And this was with Ladybug, how to analyze all the radiation in all the surface. And the yellow part that has more radiation, they wanted more fritting, less fritting, and the black part is zero fritting because it has no radiation. So, but this is architecture, it's not science. So the architect Adrià said, okay, let's make it symmetrical, even though the graphic it's not symmetrical. And we prepared like these lines, more or less like this, drawing handmade. Of this is a 10% line, 20% line, 30% line, 14, 45, all here. So how to create a pattern that goes from 10% to 45% inside this double curvature shape. Here is what I invented. It's done with Python. The point is, I assume I input some numbers here, 35, 40, 20, 20. The corners I knew, which should be the 100% of the pattern. Then I create this curve of how this grading should be, linear or curved, exponential. So I know the initial, how the pattern should be here, 27%, and it should end at 38.23%. And I know the half of it. So the point is, in Python, it was, I called it the jumping point, the running point. I have a point here. And it says, okay, I have to be at 25%. So the next point should be 25%. I move here. Where am I inside this line? I am at 10% of this line. So at 10%, I should be, next point, the gradient here should be 28%. Then let's move this. Now it should be 31%. So every point evaluates where he is, so he knows where the next one should be. And so he knows that it has to end at 38, and the same thing in the other both. So it was a running point. Every point knows where it has to go, analyzing itself once he has already jumped. And it was made in Python, and it was difficult and fun. Actually, it was really fun. How to put all these inputs, the corners, and then it analyzes itself, all these lines of points, these points here in the middle knows where they should go, and you have like millions of points in every glass panel. And you see here or the gradient, like from 10 to 20%, imagine 45%, and every panel is different, and I mean, this job without Python or Grasshopper, it's crazy and I think impossible to draw so many points. But it was really fun. Stressful and fun. And here is some details of the building. Here's when we started assembling. We had to make this zone, then this zone, then this zone, because it has to hold itself when we install it. And well, everything was perfect, but at the end, you have to make one spiral. We did assemble the nodes at the end. They pulled it backwards and then fit all together and put it back at its place and put them all. Build this spiral, disassemble then the borders, the edges, pull it back, prepare it, and boom, make some force. When they are all settled, then put some screws. So it was difficult to build. Even though it was perfect, everything was perfect, it was difficult to install it. And here that render that we saw before, here they are installing the pladur. Here is a node that you can barely see. Well, you have the joints, but I mean, it fits perfect and everything. You don't see here the big one that holds the torsion plate. And here is the image from before, that 150 node, that render from before, that everything fits. It's here. Yeah. And you can hear the pattern of the serigraphy. Even though it's a 45%, it's full of dots. You can see what it's behind, and yeah. And here it's me in the checking that everything was okay in the site. Like, okay. And well, it's just some part. Oh, you can see here the cover to this hole, to not have this hole. And well, this is it. I mean, it should be a nice presentation when it's finished, and not. But to see some parts made in Python, or the geometry, or how difficult but fun it was, yeah. And all of this was done with Grasshopper, and I did it. It's the 3D model, and it's amazing. And how we went to the consultant, say, I don't like your 3D model. It's horrible. Stop it. I will give me your surface, give me your lines that the architect want, and I will do it all by myself. Goodbye. And yeah, it was super fun to do it.
Yeah. Thank you very much, Adrià. It's really impressive. Congratulations for the job. It really looks like you're in a place where your skills are fitting very, very good. So you have like really, the last one, it's almost like printing. You have like so the Bella part, the company where Adrià is working is like a haute couture in steel construction. So they get to these contracts of very high end and very expensive jewelry project. So I think it's a very good fitting of skills and projects. So very good, looks very good. Okay, let's move forward because we are extending like a lot of the time, and everything is really, really interesting. But we need to like close at some point. Everyone has to do their own homework. So Christian, last in the today's session, so you can try to be like a little bit fast. We would appreciate it.
Okay. Hello. Yes.
Hi.
Sure. I will try to be as much as possible short. So let's start. I will share my screen. Oops. Hi everyone. So hello. I am C.Dimitri. I'm from Lebanon, and I'm from MPDA 2018. So at the moment, I'm a BIM software developer at Everse in the United States, and we do software solutions. I will explain more over. So everything started here, just like you, everyone. I accomplished my dream to study parametric design, and after finishing the master's, I joined engineering firm in Saint Cugat, and it's called Arcade Structures, and they are specialized in structural analysis and fabrication. They have Fabrica in Lleida. So the concept to hire me was that initially they have patented a node that is really economic, and bars that has a stiffness just by smashing their tip, and the node is a set of semicircles and a circle that holds every node by a screw. So the idea was to create modulars of standard shapes, like square shapes or double pitched shapes, one pitched shape or arch shapes. So initially we started everything using Grasshopper, but as the client always ask more than they think is possible, they ask 3,000 conditions. I decided to change everything to coding. Honestly, the boss, my director, didn't want me to go to write code, but the requirements that he was asking were kind of impossible to do in Grasshopper. So writing one truss in a code is much simpler than writing it in Grasshopper, and a lot of conditions can be added, cutting the articulation type to have it articulated or rigid on different type of structures, and so on. So Later, we started to extend this library from not only trusses to draw with those trusses and portiques, warehouses, and basically one modular of rectangular warehouse have served us to build an assembly of modulars. So every element was described as a class. They contain some properties related to BIM, geometrical properties, and structural analysis properties. So the idea was to be able to do a process automation from pre-design phase, which is doing simple and quick proposals by having a set of inputs, which you can have a simple method, having a simple set of inputs, and exporting the geometrical objects independently. So the outcome of this helped the engineers of the company to set the Caramba, helped me to set the Caramba definitions by setting some load cases related to the Eurocode, and everything related to geometry I was the one to modulate. So you can see on the right that only with one rectangular warehouse I was able to calculate the inputs, pre-inputs that will define the final shape. And of course, your guys using Caramba, and you can see that the visualization of the forces. So more from this library, we were thinking of a freeform surface, how we can, from a freeform surface, create a special frame of trusses. And on the right, you can see one truss from one component. Moreover, from this library as well was how to unroll panels that cover freeform bridges that comes from Tekla structures. Tekla structures is a really powerful tool for BIM modeling, execution, and so on. But as the mesh they have has a thickness, and Tekla doesn't have a plugin to unroll meshes, it has a method to unroll ruled surfaces like Grasshopper. So what I did is an interpolation between Grasshopper and Tekla using the Tekla Grasshopper link, basically by specifying one point of reference, computing, creating a connection between each neighbor face, and unrolling the first face and unrolling the rest of it inside Grasshopper, and sent back to Tekla structure to do the technical drawings. Okay, so in the meantime, I was as well managing my time to create a marketing plan for, it's a marketing objective for the company, which is a parametric user interface in the cloud computing, cloud-based application, and it's cloud computing using Shapediver. Shapediver, as you know, it's a plugin inside Grasshopper. And if you connect your outputs into the geometry loader of Shapediver and you upload your definition following the restrictions of third-party plugins that are compatible with Shapediver, you can have an online configurator. And this is good for people who want to create online e-commerce platforms to sell furniture that is parametric, like Tileco or so on. And here we created our special frames prototypes as an online configurator. And this version was actually an integration between Shapediver and Vue.js. Vue.js, it's a framework that combines HTML, JavaScript, and CSS, and it's easy to use. And basically, we designed our own user interface. On the left are the geometrical properties of the frame, and on the right are a table of the details of the spatial frame. And of course, there is the downloads for interoperability. So at the end, the architect or the contractor that is using this can download any type of file that he wants, from IFC to STL to GWG. I can show you here. So this was actually to call our clients to use and try our platform, but at the same time, this is not buildable. So we do that for them to contact us and calculate the inputs that they used using our system in Caramba internally. And we did the update with Construsoft, and we call it Optinave. And indeed, it does use Caramba, and the platform is online right now. You can go use it. And it uses the Eurocode and the United States code. I'm sorry, it is in Spanish at the moment. We are planning to implement I-18 library to be able to do quick translation. And indeed, here the system does optimize using real values and real rules. And this is they're showing how they are interoperating between Tekla and Triple Connect and so on. One real project that has been executed, I will go very quick, is a tunnel here in Spain to dissipate. It was a competition. I don't know if the company wins it. It was a set of candidates that were trying to solve the constraint of fog on a highway in the north of Spain that is causing a lot of accidents. So our company offered to do a tunnel of a spatial frame that will contain spreader of like water, but it will not be water. It's like sort of chemic, or I don't know what is it, to be able to let the fog fall down. So the assembly, they split it in two ways because the pillars are really thin. So they had to raise the corner, the sides, and assemble them from the center. So at the moment, I am really happy at where I'm working. I am learning a lot of tools how to develop for our community, a lot of software solutions, from Autodesk to Rhino to whatever our clients asks. So our goal is to change the industry and help our clients to process to automate their processes. Our team is pretty big. I recently joined the team, and we are mostly based in between Latin America, Europe, and Europe and Latin America. One of the projects that I am working on right now is for clients that calculate piles compliance for solar panels fields. I don't know if you guys know what a solar panel field is. It's a set of trackers that are supported by the piles, and each tracker contains a set of panel fields, photovoltaic panels. So each pile has a minimum and a maximum of height that can open, and the task is to optimize the quantity of material that of metal material that will be spent on the project, and a set of behavior constraints. So the thing is, initially, if they start in the XY plane on the zero height, and they have the surface of the topography at the real height of the altitude. So they do a projection, and then they specify what is the maximum slope that a tracker can have. Okay, so they raise their piles, and they measure if their piles enter inside the interval between the minimum and the maximum, and they do some sort of mathematical operation. I have it here. They find if there is a maximum difference or a minimum difference or both at the same time, and in each case there is a mathematical function that is being applied. If you see here, the piles that can't be fixed mathematically by raising the tracker or lowering the tracker, a material grading has to be made. So I will show the behavior in 3D how we did it. So basically, this is the minimum pile height, and this is the maximum pile height, and the red surface is the flood depth that a solar field can have when it rains a lot. So they do like extract some information from Earth, from how it's called? I don't remember, something topological. So they get this surface, and as well they measure those points on each pile, because the panel has to be on a certain level up above the flood. So this is a simple behavior of one pile, and this is the mathematical function for one pile, and this is the actual user interface that we created with ShapeDiver. It contains the inputs that constraints has to be set. The maximum alpha slope is how much the panel can be. Fixing grading is going to be shown right now. The blue surface is the flood depth. So the panels has to always be above the freeboard height, which is 1 meter. And this is measured on the lowest pile, and if the lowest pile doesn't match this condition, the pile has to raise. We adapted, since now it is a mock-up, we adapted a generic calculation for how much kilowatts we can extract from this panel feed, because we don't know what type of machines like inverter or and batteries and so on. So we just adapt generic inputs, which are standard numbers in the market. So if you see here, the red piles after the calculation are the piles that need to have earth below them. One of the projects as well that I'm participating in is visualizing data with IoT and Amazon Web Services using Forge and SCADA. It's a mock-up. IoT, if no one knows, it's Internet of Things and data visualization. It helps us to better understand our data, to visualize them, analyze them, and they come from different data streams. So for the one who doesn't know Autodesk Forge, it's a product that is a BIM file loader in the cloud, and it helps us to automate processes, collaborate with our teams, and automate our workflows and visualize the data. SCADA is a control, as a supervisory control. It's a sensor that as well contains compatibility with some software, some computer that can facilitate the connection between real physical life and extract it as data and visualize it. So this is one mock-up that I'm showing here right now, how we can control our motors from wherever we are, just by having one sensor and having a digital twin. We can do this not only with motors. It's a really simple example right now, but it can be done with anything. Okay, so here I wanted to show a quick sample of because I couldn't extract a GIF. So as well, our Forge viewer serves to explode the model, observe it, measure. So here you can have the layer of the IFC element. You can see them by type. You can, 1 second. You can do a cross section on the model and observe the elements. And as well, you can see the project properties. Okay, so I'll jump to the next project quickly. Okay, Argyle is not a project that I participated in, but it's a cool project that I would like to show you. It's one of our clients, and they are BIM freaks. They want to make the construction field on site like Iron Man, like Tony Stark. So I'm going to show you a video. Our role here was to help them create an exporter, a special exporter from Navisworks and Revit that can be compatible with showing and helping the co-workers on site using augmented reality on the HoloLens 2. So I'm going to show you a cool video right now. So this helps us on site, of course, to take better precision and yeah. Thank you, guys. In Everest, we do amazing things with amazing people. So feel free to reach out, and we are here to help.
Very impressive, Christian. Can you hear me?
Yes, I do.
The headphones. Okay, thank you very much, Christian. Really
Thank
nice
you.
work. I have to admit I have no idea how to do what you do, so that's always very good to see.